Okay, so this is June 2024 paper. Question number one. Oxygen has the electronic configuration 1s2, 2s2, 2p4. How are the electrons in an atom of oxygen arranged in the p orbitals? They have given us electronic configuration and they are asking about the arrangement of electrons in different orbitals. Okay, so they have given you the 2p orbital, 2p4. So 2p is a subshell and these are called orbital. This is px, this is py, this is pz. So what's the electronic arrangement in different orbitals? Yes. What should be the answer?
1s2, 2s2, or 2p4.
1s2, 2s2, 2p4. So we have four electrons. 2 plus 2, 4, 2 plus 2, 4, 2 plus 1 plus 1, 4, 2 plus 1 plus 1, 4. So all have four electrons in there in the orbital. Okay. So now the thing is that we have to think regarding the arrangement of electrons. Okay. So first of all, we have to fill the number of orbital in such a way that first of all they have to fill in a single manner. Like uh, if you remember, I told you the two rules regarding the filling of different orbitals. So let's say this is the p orbital, p subshell in which we have three orbitals, one, then two, then three. First of all, you have to fill it singly, and then one, two, three, then we have fourth electron. So this is the way in which we are going to fill electrons in different orbitals. So the answer is D. And also they are going to match with each other, but you can see this in the same orbital, electrons must have opposite spin. Otherwise, they will be repelling each other. So the orbital will become unstable. So in the same orbital, we have electrons with opposite spin. This is the same spin. So this is wrong configuration. This is right configuration. Okay. So the answer is D for doctor. Then water has the anomalous properties below. Water has relatively high melting and boiling points. Okay. Is less dense than water. Which statement explains these anomalous properties? Number one, the covalent bonding within water molecule. Remember, this is the property related to, these are the properties which is related to the IMF. Remember, I told you when I was teaching IMF, let's say I have a liquid water. So when we are going to heat that liquid water, after heating, what would be the product? So the water will remain same, but it would turn from liquid to gas. That's it. What does it mean? Only the IMF has broken down, not the covalent bonding. Only the IMF has broken down, not the covalent bonding, because the formula is the same. Only the state is different. Only the water has converted from liquid to gas. Okay, liquid to gas. So means that IMF is going to overcome between the water molecule. So in option A, they are talking about the covalent bonding. No, it's not about the covalent bond. Because if you remember when we have drawn the diagram of water molecule, so this is the covalent bond and this is IMF. Specifically, this is called hydrogen bond, of course. What is hydrogen bond? The bond between hydrogen and highly electronegative element. And how many elements we have that is going to have high electronegativity? So we have three. F O N. So O is one of them, of course. So water molecule has hydrogen bonding. Then option A is wrong. Then we have to see B. The hydrogen bonding between the water molecule. Number C, the induced dipole-dipole attraction, London forces. If you remember, we have done the differentiation between London force and the permanent dipole. When would be having London force and when would be having permanent dipole? If you have a nonpolar molecule, like hydrocarbons, H2N2, Cl2, Br2, F2, I2, At2, they are non-polar. So in these molecules, there would be London force. But if you have polar molecule, HCl, ammonia, water, H2SO4, alcohols, carboxylic acid, so they are polar. They are going to have permanent dipole. Okay, so C is wrong. C is wrong because there is no London force because water molecule is a polar molecule. A and C is wrong. Then D, the ionic bonding between the water molecule. Can you tell me why D is wrong? What's the definition of ionic bond? Electrostatic force of attraction between the oppositely charged ions, and also we know that ionic bond is only formed between the metal and non-metal. In water, there is no metal. Both are non-metals. So this is going to have a covalent bond. A is wrong. C is wrong. D is wrong. Of course, the answer is B. Of course, the answer is B. Then question three. It's related to, okay. Now, which statement explains the trend in boiling points down the halogen group? Okay, so we have done different trends across the period, down the group. So when I was telling you regarding group 2, the melting point of group 2, so we have decided that the melting point of group 2 metals decrease down the group. Why? Because as we go down the group, the size of cation increases. When the size of cation increases, okay, so its attraction between the electron is going to decrease. So less energy would be required to melt or boil the particular substance. So the melting point would be lower. And what if you have a smaller size cations? So of course, when you have a smaller cation, so it would be having a very strong electrostatic force of attraction. So more energy would be required to melt or boil the substance. But in halogens means that they are talking about group 7. They are talking about group 7. So in group 7, we have all non-metals. There is no any metal. So what's the difference between metal and non-metal? Of course, non-metals would not be having metallic bonding. Okay, so when we discuss the melting and boiling points of the non-metals, so we have to discuss on the basis of intermolecular force. And it's very easy because intermolecular forces are directly proportional to the number of electron. When the number of electrons are higher, so the IMF would be higher. When the number of electrons are lower, so the IMF would be lower. So fluorine, chlorine, bromine, iodine, and astatine. These are the group 7 nonmetals. Fluorine, chlorine, bromine, iodine, astatine. And we know that this is the gas, liquid, solid, solid. As we go down the group, number of electron increases, so the IMF increases. So the melting and boiling point increases. In option A, they are saying the bond enthalpy of the no. It's not about like let's say F Cl Br I. Whenever we melt or boil group 7 elements, so their covalent bond is not going to break down. But in all cases, remember, boiling point and melting point is the physical property which is related to the IMF. It's not about the ionic bonding or a covalent bonding or a dative bonding. Remember, it's all about the intermolecular force. So the covalent bond, it's not intermolecular force. Option A is wrong. Now B, the halogen becomes less electronegative. The halogen becomes less electronegative. It's true. It's true that when we go down the group, electronegativity decreases. Electronegativity means ability of an element to attract electrons towards itself. Of course, the size increases, so the attraction between the nucleus and electron decreases. So that's the reason electronegativity decreases. This property is like it's right, but it's not related to the melting and boiling point. It's not going to explain the melting and boiling point. That's why this option is wrong. But this statement is correct, by the way. Option C, the induced dipole-dipole interactions, like I mean to say London forces. Of course, London forces are present between the nonpolar. So they all are nonpolar. F2 is a nonpolar, Cl2 nonpolar, Br2 nonpolar. They are not going to have a charge. So I told you whenever you would be having the formula, so if you can see the different elements, so you can say the compound is polar, but if you can see the same elements, so you can say the compound is non-polar. So they are non-polar, they are going to have London forces. So as we go down the group, the number of electron increases, so the IMF increases. Like the London force increases. That's why the melting and boiling point increases. So option C is correct. D is also wrong because melting and boiling point is not related to the reactivity is something else. Melting and boiling point is something else. Okay. So option C
Okay.
is correct. Or this is related to the mole. Okay. Catalyst. Okay. 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 Yes. No. Uh, Which statement about elements in the periodic table correct? Number one, the position of an element is determined by its relative atomic mass. No, I think so. The position of element in the periodic table is exactly determined by the proton number. And of course, after looking at the proton number, we can tell the like we can write down the electronic configuration, and after writing down the electronic configuration, so I can see the group number and I can see the proton number, of course. So uh, statement one is wrong, of course. Statement one is wrong. Then we have to see. Then we have to see. Statement two: the elements in a group have similar chemical. Yeah, this is correct. Elements in the same group have the same chemical properties. Why? Chemical property is related to the number of outer electron. If the outer electrons are same, so the chemical property is same. If the outer electrons are different, so the chemical property is different. That's the reason group 1 has different chemical properties, group 2 has different chemical properties, but in the same group, whether it's group 1, 2, 3, 4, 5, 6, 7, they would be having the same chemical properties because in the same group, all elements are going to have the same outer electron. That's why. So statement 2 is correct. Okay. So then in 3, transition elements are used as a catalyst in the manufacture of chemicals. Yeah, this is also correct. So statement 2 and 3 is correct. So what does it mean? Option C is correct. That's it. Okay, so we need to know these things before going to do the periodic table. Like, of course, periodic table means they would be asking down the group, they would be asking across the period. So each and everything we need to know. Or let me see other questions which is related to no. Okay. Yes, okay, but this is related to the chemical property. I want to do only the trends and that's it. Yeah, this is related to the melting point that I have told you. The table shows the melting points of some of the elements in period 3 of the periodic table: aluminium, silicon, phosphorus, and sulfur. Aluminium is 660, silicon is 1410, P4 is 44 only. It's two digit. S8 is 119. Of course, we have discussed that metals are going to have high melting point as compared to the non-metal, and this is true in that case. Silicon is not following the trend because it's going to have a giant covalent structure. So that's the reason silicon would be at the top of the periodic, like in the period tree, of course. So explain the melting points in terms of bonding and structure. So first of all, let me tell you the bonding and structure. So now aluminium, aluminium is going to have metallic bond. Aluminium is going to have metallic bond. Okay. Aluminium is going to have metallic bond. So, and silicon is going to have a giant covalent structure. Silicon is going to have a giant covalent structure. Then P4 is a simple molecular structure. It's not giant covalent. Okay. It's a simple molecular structure. Or S8 is also has a simple molecular structure. Okay. So I am supposed to write about the sulfur, about the aluminium, that it's going to have giant metallic lattice structure. Okay, it's going to have a giant metallic lattice structure. And in this, there would be a strong metallic bonding. Strong metallic bonding. Strong metallic bonding. And of course, metallic bonding is the electrostatic force of attraction between the cation and C of delocalized electrons. So due to that, more energy would be required to melt or boil aluminium. That's why it's going to have higher melting and boiling point, of course. Then about silicon. So silicon means that it has a giant, it has a giant covalent structure. So when it is a giant covalent structure, so a lot of covalent bonds are there. A lot of covalent bonds are there. That's the structure for silica, like silicon. I can say that uh, this is like that. Silicon, 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 and silicon. Each silicon is bonded with four other silicons, and a lot of silicons are there. So there would be a lot of covalent bonds. So of course, more energy would be required to melt or boil silicon. That's why it has a it has a highest melting point across the period tree. Then P4 is a simple covalent. P4 is a simple covalent like that. Simple molecular, or I can say simple covalent structure. Okay. And it has less number of electron. Okay. It has less number of electron. So due to that, it has weaker it has weaker induced dipole attraction. So that's why less energy would be required to melt and boil. And if you discuss the sulfur, it's going to have the same trend. It This is also simple covalent structure, but it has a stronger London force. Why it has a stronger London force? Because it has more electrons. Okay, because it has more electrons, and when it would be having more electron, so there would be more attraction. So that's why the melting and boiling point of sulfur would be higher than that of phosphorus. That's the comparison. That's the comparison between the melting points from period 3 between metal and the non-metal. So this is non-metal, metal, and It's somehow different. It's a giant covalent structure. Okay.